Yo, 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 yo. Yo. All right, guys. Exponential functions. So we're going to get out there right now. We got a lot to talk about, a lot of pieces here. So exponential functions, we have key terms. We have an asymptote. Okay, we have a constant ratio. We have an exponential function. Now, asymptote, that is a line that a function approaches but never touches. I will show you an example of that when we get to graphing our first one. Constant ratio, we'll get to that after our first example as well. And an exponential function is just what we're working on today. So here is your formula for exponential functions. And let's just start looking at examples right now because that helps me explain everything. So an exponential function is f of x equals 2 to the power of x. Okay, this is an example of an exponential function. So we have a base that is a numerical value, and our variable is the actual exponent. So let's see what happens by making a table. That's how we've always shown how what happens to graphs and what they look like. So I have some values here. We're going to plug it in and see what they equal. So when I use x value for -2, I'm picking random points just to show you the shape of an exponential function. So 2 raised to the power of -2, well, that's the same thing as 1 over 2 to the power of 2, because that's a negative exponent, which is 1/4. So when x is -2, y is 1/4. It's right there. It's right above 0, right? That's an estimation. It's an approximation. It's not a perfect point, but that's pretty close. So now let's do the same thing when we have 2 raised to the power of -1. Well, that's 1 over 2 to the power of 1, which is just 1/2. So when we're at -1, we're at 1/2. So we should be a little bit higher than that first one. 2 raised to the power of 0, we know that's 1, so that was easy. Because anything raised to the power of 0 is 1. So when x is 0, my y is 1. 2 raised to the power of 1, well, that's 2. 2 raised to the power of 2, that's 4. And 2 raised to the power of 3, that's 8, because I'm multiplying by 2 each time. So let's graph those points. So when I'm at 1, my x value is 2. When I'm at 2, my x value is 4. And when I'm at 3, my x value is 8. 1, 2, 3, 4, 5, 6, 7. So that's like up here. So we started off barely going up, and then we went up more, and then more, and then more, and then a lot more. This is what an exponential function looks like. And if I keep going this way, it's going to keep getting closer to 0, but it's never going to get to 0. It's never going to touch 0. The reason why is, let's think about that. No matter what negative value I pick for x, I can pick -100. Okay? So if I have an x, it's all the way over here. If I put -100, 2 to the -100 is 1 over 2 to the 100th power. Now, 1 over 2 to the 100th power, that's going to be a positive number, and it's going to be greater than 0. It's going to be a tiny, tiny number. It's going to be like 1 over 1 million. So it's going to be like the smallest fraction, but it's still greater than 0. So this line will never touch 0, but it'll go on forever, getting closer and closer to 0 without touching it. And then it'll go this way, and it's going to increase more and more the further we go. So this is the shape of an exponential function. Now let's talk about some of the properties here. An asymptote, as we looked at the definition, it's a line that we approach but we never actually touch. The asymptote here is y equals 0. Okay? So the asymptote, I forgot the m. Oops, there we go. Spaz, sorry. So the asymptote here is y equals 0, because this line is approaching y equals 0, but it's never going to touch 0. So that would be the asymptote. Okay, so it's the equation of a line, and that's a horizontal line at y equals 0. We also have domain still. That's still a thing. Okay, the domain for this one is all real numbers, as domain a lot of the times is. Our range, well, if it's approaching the asymptote, if the asymptote's at 0, so that means the range has to be anything that's greater than, or anything that's greater than 0. Can't be or equal to. My apologies. Anything that's greater than 0, because it's never going to equal 0. Has a y-intercept of 1. Okay, and there we have it. Now, that's it. This is the shape. Let's look at another example here. So a network administration uses the function f of x equals 5 to the power of x to model the number of computers a virus spreads after x hours. So if there are 1,000 computers in the network, about how many hours will it take for the virus to spread to the entire network? Okay, so again, we're going to plug in our values. So we're going to have start out here at 0. So 5 to the power of 0 is 1. There's my first point. 5 to the power of 1 is 5. So 5 to the power of 1, why was that 1 here? That's going to be 1, 2, 3, 4, 5. Well, right away, if we notice, is it possible for me to graph all this on here? No. Okay, because this is going to be all the way up here at 25. So that's why we might have to change our y values in our graph, and we're going to have to actually we're not going to be able to count by ones here. We're going to have to count by something else. So instead of counting by ones, I'm going to erase these points. Let's just count by 100. And you'll see that that's going to help me out quite a bit. I'm still not going to be able to fit all these points on here, but that's okay. It'll still show you the shape. So now if I'm counting by 100, that means we're going to be really close to 0, right? I mean, it's hard to really show that 0, 1 point. It's also really hard to show it right here at 1, 5. And even here at 125, it's really hard. At 225, it's really hard to show. But I can show that it's increasing a little bit. Now, when I get 5 to the 3rd power and I get to 125, it's going to start getting a little bit easier, okay? Because that's right here above 100 at 125. Then when I multiply by 5 again, I'm going to be at 625. That's 5 to the 4th power. So that's why I counted by 100s, because it increased. It jumped a ton. And now we're up here. So the shape, it's again increasing dramatically. And it'll go on forever this way, but it's never going to hit 0. Okay? And then 5 to the 5th power. 5 to the 5th power is 3,125. Now, what we would want to do is, if I had a better graph of this, I would want to see, well, about where is it going to hit 1,000 on my graph? Okay, and that's where we're going to make an estimation, then we're going to use a calculator to guess. My estimation would be about 4.3, 4.2. And what I would do is I would use a calculator and I would do 5 to the 4.3 power, okay, and see what I get. 5 to the 4.3 power, that's 1,012, okay, 0.91, which is really close to 1,000. And so that would be a reasonable answer, that it would take about 4.3 hours. Okay, but I know it's in between 4 and 5. It's got to be a lot closer to 4 than a 5. Based on this value and the difference between the two. And if we had our graph and we had a better graph to show that, I'd be able to use that estimation and use a calculator just to check to see if my estimation was reasonable. Okay. So one thing I want to talk about here, asymptote is at y equals 0. Okay, domain still all real numbers, range is still y is greater than or greater than 0. One thing I want to talk about is constant ratio. That was one of your vocabulary terms. The constant ratio is you take the consecutive y values and you divide them. So if I take these two values right here, I divide 25 over 5, I get 5. If I do these two values, 125 over 25 is 5. If I look at these, 3,125 over 625 is 5. A ratio is a fraction. So we're taking the consecutive y values, and the second one's always on top, and the one before it's always on the bottom. And that is giving you your constant ratio, which, if you notice, is this value right here that we're raising our power to. And that goes back to our formula here, where the b value raised to the power of x, that is the value of the constant ratio. So that's how we write something in exponential form. Okay, that's how we write an exponential function, is we find that constant ratio, and then we figure out, well, what is the initial amount when x is 0? Okay. So for this one right here, my initial amount when x is 0 is 4. So for this function, when x is 0, we have 4. So that's our starting value. If we notice on these last ones right here, at 0 we were always at 1, right? So that was times 1. Well, we don't need to write times 1 ever. So that's why we didn't have 1 there. But this one, when we're at 0, we're at 4. So it'd be 4 times whatever my constant ratio is. Well, what's being multiplied by every single time? Well, 36 divided by 12 is 3. 12 divided by 4 is 3. 108 divided by 36 is 3. So that'd be 4 times 3 to the power of x. So this would be the exponential function for this particular function. Okay. Now, let's go to the next one. So I want to write an exponential, I want you guys actually to write an exponential function for each set of points. Write it for A and write it for B, please. So write it for A and write it for B, and I think you guys will be just fine. So write it for A and write it for B. Okay. So for A right here, initial value, when we're at 0, we're at 3. Okay, so if we're at 0 and 3, then I know it's got to be f of x is equal to 3 times, and then now I got to do 12 divided by 3, which is 4. That's 4x. 48 divided by 12 is 4. 192 divided by 48 is 4. I'm done. Second one right here. Our initial value is 2,187. I know it looks kind of confusing with the commas, but that's 2,187. So that's my initial value. So that's where I'm going to start at, 2,187. And that's times, well, now I got to do my constant ratio. Well, that's 729 over 187. Or I could also look at it as 81 over 243, or 27 over 81. And this is the one that's really easy to look at. That's 1/3 raised to the power of x. Now, if we did the division, you would have gotten 0.3 repeating, which is fine, but the fractions are more accurate. So 0.3 repeating as well, raised to the power of x. But a fraction's a more accurate representation, and that's going to show me that my ratio is always going to be 1/3. And it's okay to have this, because this is an example of exponential decay, and the difference with this graph is we're going to start really high, and then it's going to get smaller each time. So it's going to look like this. So it's the same shape, but going backwards. Okay? And we'll get more into this later on. All right, so now what I want to talk about is I want you to compare these two pledges for donating to charity. So we want to see which one's going to increase the pledge amount faster over time. So I have option A and option B. I want you to fill out the tables, and then I want you to answer the question. And you can actually even write me a function for each table. So write me a function for option A, function B, and we can talk about the differences. So option A, $100 for the first week, and each week after that, the amount increases by $25. So we'll go $100 for the initial amount, and then we're increasing by 25. So it's 125, 150, 175, 200, and 225. So if I were to write a function, this is not an exponential function, because if I did 125 divided by 100, it's not going to be the same thing as 150 divided by 125. It's not a constant ratio. I'm not multiplying. I'm actually adding. So because I'm adding, this is a linear function. This has a slope of 25, and we started at 100. This one right here, so it was $1 for the first week, so we started at $1, and then we tripled it each time. Okay, well, if we times it by 3, that's tripling it. So we go to 3, 9, 27, triple that, 81, triple that, we're at 243. So by 5 weeks, this person started with $100, this person started with $1, but this person ended up with 243 after 5 weeks. This one ended up with 225. And that's the difference with exponential functions, is they increase much, much faster. Okay, and even if you start at a low amount. So this function would be 3 to the power of x. Okay, so linear, exponential is going to increase a lot faster. All right, that's all I got for you guys. So we're going to leave it at that. For things to remember, I would say constant ratio is the second y value, or it's the best way to write it. Constant ratio, and I'll draw an example of it actually. So I'll go 0 and 3 and 1 and 6. So just to show an example, is 6 over 3, which equals 2. Okay. All right. That's all I got for you guys. I hope this helped. If you guys have any questions, please let me know. we'll get some practice on this. Grady is out.